So we are continuing our discussion of rings. And what we talked about on Monday was the subjects of quotient rings, ideals, and ring homomorphisms. So let me just review that. So we say that R be a ring. A subset I of R is what is called an ideal if first I is an additive subgroup of R. Remember, a ring has addition and multiplication. With respect to addition, the ring is an additive abelian group. So I is a subgroup of R is an additive abelian group. And second, for all elements X in the ideal and all elements R in the ring, if you take X and multiply it on the left by R, that's still in the ideal. And if you take X and multiply it on the right by R, this is also in the ideal. So this is what is sometimes called a two-sided ideal, because elements in the ideal stay in the ideal if they're multiplied either on the left side or on the right side by an element of R. And given an ideal I, the set of left cosets R mod I, which is the set of everything of the form R plus I for all R in the ring. So this we know is this is an additive abelian group. This is the quotient group. But this is also a ring with the well-defined multiplication of cosets. If you have R plus I times S plus I, we can unambiguously call that the ideal RS plus I. That's the multiplication. And so we get a ring. So this is the quotient ring. And the classical example is if you take the ring Z of integers and the ideal I to be the set of all multiples of some positive integer M, then we have the quotient ring Z mod MZ, which is what we've seen already, the ring of congruence classes modulo M. So this is the simplest and most fundamental example of a quotient ring. Any questions about this? So let's look for another minute or two at these rings of congruence classes. Suppose we let R be the congruence classes mod 4. So this consists of the 4 cosets, the multiples of 4, 1 plus 4z, 2 plus 4z, and 3 plus 4z. So this ring consists of these 4 cosets. These are all the numbers, the integers divisible by 4. This is everything which is 1 mod 4, everything 2 mod 4, everything 3 mod 4. And multiplication is defined by m plus 4z times b plus 4z is ab plus 4z. Right? That's our multiplication. And we notice in this case that, for example, 2 plus 4z is not 0. 0, the additive inverse, the additive identity is 0 plus 4z or 4z. So this is non-zero. This is a non-zero element in this ring. But what happens if we multiply 2 plus 4z by itself? We get 2 times 2 plus 4z. 2 times 2 is still 4. And 4 plus 4z, 4 is 0 mod 4. So this is the same as 4z. In other words, if we let, we call this x equal 2 plus 4z, x is different from 0, but x times x equals 0 in this ring, z mod 4z. So you can have a non-zero element, but you multiply it by itself, you actually get 0. That's an awkward thing. Let's look at another example. Suppose I let R be equal to the integers mod 6. So we have the 0 congruence class, 1 plus 6z, and so forth, up to 5 plus 6z. Right? There's 6 elements in this ring. Each element is a coset. And 2 plus 6z is not 0. And 3 plus 6z is also not 0. But if I multiply, suppose I call this x and I call this y. X times y, it's the product of these 2 congruence classes. 2 plus 6z times 3 plus 6z. That's 2 times 3 plus 6z. 2 times 3 is 6. And 6 plus 6, 6 is 0 mod 6. So this is 0 plus 6z. In other words, x is different from 0, y is different from 0 in this ring, but xy equals 0. Right? So it can happen very easily in a ring that the product of 2 non-zero elements is 0. This cannot happen in the integers, right? So for example, in Z, the ring of integers, if x is different from 0 and y is different from 0, then xy is different from 0. And rings that have this property are very nice, and because we can do more things like arithmetic in them. So this leads to the following definition. A commutative ring R, commutative means xy equals yx. For all x and y, multiplication is commutative. A commutative ring R is what is called an integral domain. So this is the term we're defining. If x in R, x different from 0, and y in R, y different from 0, implies the product xy is not equal to 0. That is, if the product of two non-zero elements stays non-zero. So Z is an integral domain. Z mod 6Z is not an integral domain. Because, for example, we saw in this ring, the congruence classes of 2 and 3 are non-zero, but their product is 0. So the integers form an integral domain, but the congruence classes mod 6 do not. If you check the arithmetic, if you look at, for example, Z mod 5Z, this is an integral domain. Because if you take any two non-zero congruence classes mod 5, their product is non-zero mod 5. And you can see that actually just by looking at the multiplication table.
Professor, is it too easy to just think if it's a prime, then it would be an integral domain, the number?
Right, so that's actually a theorem. So Z mod PZ is an integral domain if and only if P is prime. Right? But that's a statement that needs to be proven. Right? So let me just finish this example. If you have the multiplication table for Z mod 5Z, so let me just use 0, 1, 2, 3, and 4 to represent congruence classes. 0 times anything is 0. 1 times anything doesn't change the anything. 2 times 2 is 4. 2 times 3 is 6 is 1. 2 times 4 is 8 is 3. 3 times 2 is 6 is 1. 3 times 3 is 9 is 4. 3 times 4 is 12 is 2 mod 5. 4 times 2 is 8 is 3 mod 5. 4 times 3 is 12 is 2 mod 5. 4 times 4 is 16 is 1 mod 5. So this little square of numbers inside the multiplication table, these are the products of all possible pairs of non-zero elements. And you see there's no 0 in this box. That is, the product of two non-zero elements, non-zero congruence classes in the integers mod 5 is never 0, right? There's no 0 in this box. So related to a ring being an integral domain is what is called the cancellation property. R is a ring with cancellation if it has the following property. If for all x, y, and z in the ring, if x is different from 0 and xy equals xz, then you can cancel the x and say that y equals z. So you need this condition, x different from 0, because if x is 0, 0 times any element of the ring is 0. So 0 times y is 0, 0 times z is 0. And y doesn't have to equal z. But if x is different from 0, then if xy equals xz, if the ring has cancellation, then you can cancel the x and you get y equals z. And let's say R is a commutative ring, so I don't have to keep writing commutative. So a commutative ring is an integral domain if and only if that ring has cancellation. And the proof goes as follows. So suppose R is an integral domain. Then R be an integral domain. That X, Y, Z be in R with X not equal to 0. If X, Y equals X, Z, then X, Y minus X, Z is 0. Right? If X, Y equals X, Z, then you subtract X, Z from both sides. You get 0 as X, Y minus X, Z. But I can factor out an X because the distributive laws hold in a ring. This is X times Y minus Z. But in an integral domain, the product of two non-zero elements is non-zero. Here, we know X is non-zero, and X times Y minus Z is 0. So the only way X times something can be 0 means Y minus Z must equal 0, or Y equals Z. In other words, you can cancel the X. So every integral domain has cancellation. If XY equals XZ, then XY minus XZ is 0. But I can factor out the X on the left. This is X times Y minus Z. And if the product of two elements is 0 in an integral domain, at least one of the elements must be 0. We know X is not 0. So Y minus Z has to be 0, so Y equals Z. So this is the proof of the statement from left to right. If you have an integral domain, then you have cancellation. And how do we prove the converse? Suppose R is a ring that has cancellation. That is, this cancellation property is satisfied. Suppose we have XY equals 0 and X is not 0. Then we have to show Y is 0. Right? We have to show that a product of two elements is 0 if and only if at least one of them is 0. So that XY equals 0, if X is 0, we're done. But if X is not 0, then you have to show Y is 0. But if X is not 0, then X times Y, which is 0, that's what we're given. But 0 is also X times 0. So X times Y equals X times 0, and X is different from 0. So you can cancel the X. And when you cancel the X, you get Y equals 0. So R has to be an integral domain. So in a commutative ring, this property of being an integral domain is equivalent to the ring having this cancellation property. And that is a useful fact. So we've defined one type of ring, which is an integral domain. There's another type of ring, which is called a field. So a field, so let's, let me just make a few more definitions. That R be a ring, a unit in R is an element U in the ring that has a multiplicative inverse. That means there exists an element V in the ring such that U times V and V times U equals 1. Right? So it has an inverse. So for example, in the integers R, x equal 2 is not a unit, or U equal to 2, x equal 2, is not a unit. I'll call it U. Because U times V, or 2V, is not equal to 1 for all integers V, right? So U, the number 2 is not a unit in the ring of integers because there's nothing you can multiply by 2 that gives you 1. On the other hand, in Z, U equal to -1 is a unit because if you let V be -1, UV and VU, this is -1 times -1, they're both equal to 1. So -1 is a unit, but 2 is not. And okay. So let U be an element in R and let V1 and V2 be elements in R such that UV1 equal V1U equals 1 and UV2 equals V2U equals 1. So U is definitely a unit, and we have two elements, V1 and V2, that satisfy our conditions. And what can I say about V1? V1 is, of course, V1 times 1, because 1 is the multiplicative identity. And 1 can be written as U times V2. By associativity, V1 times UV2 is V1U times V2. But V1U is also equal to 1, and 1 times V2 is V2. So V1 equals V2. So if U is a unit, there's a unique element V which satisfies this equation. It's called, so if U is a unit, what is called the inverse of U, which we know there can be only one, and we can write it as U to the -1, is unique. So every element that has an inverse has a unique inverse. So that R be a ring, and let, I'll write it as R with a superscript times sign, be the set of all units in R. So note, first of all, if I take U equal 1, 1 times 1 is 1. So 1 is a unit. So the identity 1 is always in this set of units. If U and V are both units, then if I multiply UV, and I multiply that on the right by V inverse U, the V's and then the U's cancel, I get 1. And similarly, V inverse, this should be a U inverse, V inverse U inverse times UV is also equal to 1. So UV is a unit. So the product of units is a unit. And U inverse U equal U, U inverse equal 1 means U inverse is a unit, And the inverse of U inverse is just U. So this set of units in a ring is closed under multiplication, contains the inverse of each of its elements, contains 1. So this is always a multiplicative group. So sitting inside of any ring is this object called the group of units. So let's do some computations. Let's compute the group of units for the following rings. I should also make one observation. 0 is never a unit, because 0 times any element is 0. It's not equal to 1. So the group of units never contains 0. 0 cannot be a unit. Suppose I take the integers. So 1 is a unit and minus 1 is a unit, and that's all there are, right? If m is an integer and m is not equal to 0 or plus or minus 1, then mv is not equal to 1 for every integer v. There's no integer. I mean, m is at least 2 in absolute value. So no multiple of m is equal to 1. So the group of units in the integers just consists of plus 1 and minus 1. Suppose R equals Q, which is the set of rational numbers, fractions. So if U is in Q, then U is a fraction. It's A over B for some B not equal to 0. If U is not 0, then A is not 0, right? U is 0, a fraction 0, only if the numerator is 0. Denominator can't be 0. So suppose you take a non-zero fraction, a non-zero rational number. Suppose we let V equal B over A, which is another rational number, because A and B are non-zero, so B over A is rational. UV is A over B times B over A is 1. So U is a unit in Q. In other words, in the rational numbers, the group of units is all non-zero fractions. That is, all the rational numbers with 0 removed. So in the rational numbers, every non-zero element is a unit. Let's look at another example. Suppose I take R to be the integers mod 6. So we know that 1 plus 6z, this is the identity, this is the number 1, right? 1 plus 6z times 1 plus 6z is 1 plus 6z. So 1 plus 6z is in the group of units of this ring. 5 plus 6z times 5 plus 6z is 25 plus 6z, but 25 is congruent to 1 mod 6, so this is 1 plus 6z. So 5 plus 6z is also a unit. But you can check 2 plus 6z, 3 plus 6z, 4 plus 6z. These are not units. There's no multiple of 2, 3, or 4 that gives you 1. So for the ring 6 mod 6z, z mod 6z, the group of units consists of just the congruence classes 1 plus 6z and 5 plus 6z. So that's a calculation of the group of units. Any questions about this? Let's look at another example. Suppose I take the integers mod 5. So I know that 1 plus 5z times 1 plus 5z is 1 plus 5z. 2 plus 5z times 3 plus 5z is 6 plus 5z, but 6 is congruent to 1 mod 5, so this is 1 plus 5z. So this says 1 is a unit, 2 is a unit, 3 is a unit. 4 plus 5z times 4 plus 5z is 16 plus 5z. Again, 16 is congruent to 1 mod 5. So this is 1 plus 5z. So in the ring of congruence classes mod 5, the group of units is all the non-zero congruence classes. 1 plus 5z, 2 plus 5z, 3 plus 5z, 4 plus 5z. Or in other words, it's the whole ring, z mod 5z, with only the congruence class of 0 removed. So in the integers mod 6, only 2 of there are 5 non-zero congruence classes, but only 2 of the 5 are units. In the integers mod 5, in that ring of congruence classes, there are 4 non-zero congruence classes, and every one of those 4 elements is a unit. And those are really the simplest imaginable rings where everything is a unit, and they're called fields. So a field is a commutative ring such that every non-zero element is a unit. We call the ring F, that is, the group of units is F with only the number 0 removed. So z mod 5z is a field. The rational numbers is a field. The integers themselves is not a field. Z mod 6z is not a field. Right? So a field is a ring a commutative ring where every non-zero element is invertible, has an inverse, is a unit. And I can make the following observation. Every field is an integral domain. So if you have a field, it's automatically an integral domain. Why is that? And so if x, y are in F, x comma y, and x, y equals 0, then either x is equal to 0 or x is not equal to 0. If x is not equal to 0, then x is a unit because we have a field. And if I take x, y equals 0, and I multiply this equation on the left by x inverse, I get x inverse xy is x inverse 0. But x inverse x is 1, so this is just y, and anything times 0 is 0. So if x is different from 0, then y has to be equal to 0. So in a field, if a product of two elements is 0, at least one of them is 0. Right? So every field is automatically an integral domain. And the ring Z of integers shows that an integral domain is not necessarily a field. Okay. But now, if you just go back to elementary school, you remember that in the beginning of elementary school, you have the integers. And then after a while, you started with the positive integers and maybe 0. And then you learned about the negative integers. And as you progress through elementary school, you went from the integers to fractions. Numbers like a half, 2/7, minus 8/5, and so on. Or another name for a fraction is a rational number. So we started from the integers and we went to the rational numbers. Somehow we have the integers, and then you look at these expressions, which are like one integer on top of another. Those are the fractions. And in the integers, you can't always divide one integer by another, but in the fractions, in the rationals, you can always divide one rational by another and get another rational number. And there was a process of construct rationals from integers. Like you could say a rational number was something of the form a over b, where a and b are integers and the denominator is not 0. But then you also had something like maybe a over b, but what about ac over bc? You wanted to say that even though these look different, they somehow represented the same fraction, like 1/2 and 7 over 14. You want to say they're the same, even though here the numerator is a 1 and here the numerator is a 7. Here the denominator is 2 and here the denominator is 14. So how can you say that these two fractions are the same. So, I mean, your teachers probably didn't tell you this in as much detail as I am, but you would sort of say these are the same because when you cross multiply, 1 times 14 equals 2 times 7. Right? That's what you mean by saying these two fractions are the same. In other words, you would say A over B equals C over D. So A, B, C, D are integers, and the denominators are not 0. These are equal if AD equals BC. So if you think about how you learned arithmetic, and I have no idea what grade they teach you about fractions, but however you learned arithmetic, that somehow they taught you that this is how you tell if two fractions are the same. You know, like 10 over 35 is equal to 6 over 21, because 10 times 21 is 210, and 6 times 35 is also 210. So that's how you know these two fractions are equal, right? How do you know that 30 over 93 is not the same as 40 over 62? Or even let's make it 42 over 62. How do you know these are different? Well, you know they're different because if you multiply 30 times 62, you get, what do you get? You get 1,860. And if you multiply 42 times 93, well, whatever it is, you don't get a 1,860. So that's how you know that these two are different. Right? That's right. Okay, so in general, the process of constructing the rational numbers or the fractions from the integers, we could do that algebraically because the integers formed what is called an integral domain. And so we want to sort of copy this in the much more general abstract algebra setting, so that R be an integral domain. Our goal is to construct what we would call the field of fractions F of R. So F is going to be a field that contains R and is, in some sense, the smallest field that contains R. That is, every field that contains R must also contain this field of fractions. That's what sort of what we mean by the smallest. Okay, so this is going to be a construction. So for now, instead of writing A over B, I'm going to look at ordered pairs, A comma B, with A in the ring and B in the ring, but not 0. So I'm going to look at all ordered pairs, A comma B, where B is different from 0. So it's going to be the case that A over B is what we're going to call the fraction A divided by B. There's A comma B is going to be A over B. But we need to deal with the fact that you can represent the fraction in two different ways, like 2 over 4 is the same as 1 over 2. So I want to define a relation on these ordered pairs. We'll say A over A comma B is equivalent to C comma D if AD equals BC. So this is a relation on ordered pairs of elements of the ring. And I claim this is an equivalence relation. So I have to show, first of all, it's reflexive. So AB does equal BA, which means that the pair A comma B, sorry, this is symmetric, the way I've written it, this is symmetric, is equivalent to BA, right? These are equivalent if AB equals BA and the ring is commutative, an integral domain is commutative, so this is satisfied. This is also, let me squeeze it in over here, reflexive. A comma A is equivalent to itself. Because A times A equals A times A not equal to 0. Actually, let me do this on a clean sheet of paper so I have more room. So we're looking at the set of ordered pairs, A comma B, where A is in the ring and B is a non-zero element in the ring. So we have the set of ordered pairs. And we define a relation. AB is equivalent to CD if AD equals BC. So that's some relation on these ordered pairs. So I want to prove it's reflexive, symmetric, and transitive. So I want to show that every element is related to itself. That's reflexive. This is true because AB equals BA. The ring is commutative. So every ordered pair is related to itself. If AB is related to CD, that means AD equals BC, which is the same as saying that CB equals DA, which is the same as saying the pair CD is related to the pair AB. So AB related to CD means CD is related to AB. And if AB is related to CD and CD is related to EF, this means what? So this is a little bit trickier. If AB is related to CD, AD equals BC. And if CD is related to EF, that means CF is equal to DE. So if AD equals BC, that means that if I multiply by F, ADF equals BCF. And if CF is equal to DE, if I multiply by B, I get BCF equals BDE. I'm multiplying both sides of this equation by B. I'm multiplying both sides of this equation by F. So ADF is BCF, BCF is BDE. These two are equal. So if I put that together, that says that ADF equals BDE. And D is not zero because the second coordinate of one of these ordered pairs is not zero. So I can cancel. But I can cancel D from this equation because we have an integral domain. We have cancellation. So that says that AF equals BE, and that says exactly that the ordered pair AB is equivalent to the ordered pair EF. So if AB is equivalent to CD and CD is equivalent to EF, then AB is equivalent to EF. So that's transitivity. So therefore, this relation, the squiggle, is an equivalence relation. So what I've just done is the following. Given an integral domain R, that is a commutative ring with cancellation, we constructed an equivalence relation on the set of ordered pairs A comma B, where A, B are in R, and B is not zero. So for any ordered pair, let me put in like in square brackets that this be the equivalence class of the pair AB. That means this equivalence class consists of all ordered pairs CD such that CD is equivalent to AB. Or if you like, the set of all ordered pairs CD such that AD equals BC. Right? This is this equivalence class. So let's look at some examples. Suppose I take R to be the ring of integers. What is the equivalence class of 2/3? So this is all ordered pairs CD such that 2D equals 3C. Which, if you like, is the set of all ordered pairs CD, and D different from 0, of course. Second coordinate is always 0. 2D equal 3C means the same as saying that C over D equals 2/3. So in elementary school language, this is all fractions that when you reduce them to lowest terms, give you 2/3. That's what this equivalence class looks like. What's the equivalence of 0, 1? That's all CD such that 0 times D is 1 times C, which is the same as saying all pairs CD with C equal to 0. This is a set of all pairs 0, comma D, where D is not 0. That's the equivalence class of 0, 1. What would the equivalence class of 1, 1 be? It would be all ordered pairs. I can write, it doesn't matter what letters I use, A, B, such that 1 times B equals 1 times A, or in other words, A equal B. So this is all ordered pairs of the form A comma A, where A is a non-zero integer. And again, this corresponds to the fact that this is all fractions A over A equal to 1. Right? All the ways you can write 1 as a fraction, you can write 1 as 2 over 2, 3 over 3, 500 over 500. That's this equivalence class. And so what I would like to do is I want to make this set of fractions, these equivalence classes, into a field. I need to be able to add and multiply them. I want to define addition and multiplication of these equivalence classes. So multiplication is probably easier. Let's start with that. Suppose I would like, so suppose AB is equivalent to A prime, B prime. And CD is equivalent to C prime, D prime. So this means that AB prime equals A prime B, and this means CD prime equals D prime C. Sorry, CD prime equals D C prime. See, how will we, let's just sort of keep in mind what we're trying to do. What they teach you in elementary school is that A over B times C over D is AC over BD. So we want this kind of multiplication of fractions to continue. So what I claim is, so what we would like is, what would we like? Would like that if I take AB, that equivalence class, and the equivalence class of CD, that's the equivalence class of AC comma BD. Exactly what you learn in elementary school. So I want to claim that ACBD is equivalent to A prime C prime comma B prime D prime. So that when I'm multiplying equivalence classes of these ordered pairs, it doesn't matter what representative I choose. So this is true. Let's see if we can do the arithmetic. If and only if AC B prime D prime equals BD A prime C prime. Right? Which is true if and only if, let's see, the difference is 0. So this minus this, let me write it as, I don't know, A B prime C D prime minus A prime B C prime D. We want that to be 0. And I know that AB prime is A prime B. So this is equal to AB prime, this is A prime B, C D prime minus A prime B, C prime D. And if I factor out this A prime B prime, so A prime B, I get A prime B times CD prime minus C prime D, but CD prime minus C prime D, right, C prime D, they're equal. So this is 0, so we win. So this says that multiplication using the rule AB times CD equals ACBD is well defined. We get the same equivalence class no matter what way, what representatives of each of these equivalence classes we choose. So this gives us a well-defined way to multiply equivalence classes. And what about addition equivalence classes? Again, we copy what we learned in elementary school. In elementary school, you learn that A over B plus C over D is AD plus BC over BD. So this is what we have as our model. And we would like to define the equivalence class of AB plus the equivalence class of CD to be the equivalence class of AD plus BC, comma, BD. And the question is, or what we have to show is, show this is well defined. That means that suppose A prime B prime is equivalent to AB and C prime D prime is equivalent to CD. We have to show that A prime D prime plus B prime C prime, comma, B prime D prime, that ordered pair is equivalent to AD plus BC, comma, BD. We have to show these two ordered pairs are equivalent if these conditions are satisfied. So the only way to do that is to show this times this, A prime D prime plus B prime C prime, times BD equals B prime D prime times AD plus BC. Or equivalently, that 0 is equal to the difference, this minus this. So let me just see if I can work it out in one long equation. When I distribute this across, I get A prime D prime BD. I get A prime B D D prime plus B B prime C prime D minus this, which is A B prime D D prime plus B B prime C D prime. And if I look at this very carefully, here I have a DD prime and here I have a DD prime. If I factor that out from these two terms, I have A prime B minus AB prime DD prime. And from these two terms, I can factor out a BB prime. So plus BB prime, C prime D minus CD prime. But this is 0. These are related. This says that A prime B equals AB prime. These are related, so C prime D equals DC prime. So I get 0 times DD prime plus 0 times BB prime. That's 0. So this is a well-defined addition of these congruence classes. So what I need to show is that the set of equivalence classes is a field with all of these, with these definitions of addition and multiplication. And that, is there a question? Right. So that just means we have to do a lot of work. So let's look at addition. Our rule is that the equivalence class of AB plus the equivalence class of CD is the equivalence class of AD plus BC, comma, BD. So is this associative? Is this addition associative? So we have to show that if I take the equivalence class of AB plus the equivalence class of CD and add to it the equivalence class of EF, that's equal to the equivalence class of AB plus the equivalence class of CD plus EF. So let's just check that. What is on the left-hand side? This is the equivalence class of AD plus BC, comma, BD, plus the equivalence class of EF. So this is the equivalence class of AD plus BC times F, comma, BDE. That's the left-hand side, which is the equivalence class of ADF plus BCF, comma, BDE. And now let me calculate the equivalence class of this right-hand side. So on the right-hand side, we have the equivalence class of AB plus the equivalence class. When I add these two, I get CF plus DE, comma, DF. And now when I add these two equivalence classes, I get A times CF plus DE plus, sorry, I get A times DF A times DF plus B times CF plus DE, comma, BDF. So that's the equivalence class of ADF plus BCF plus BDE, comma, BDF. Let's see, when I added these, I left out a term. This is AD plus BC times F plus BDE and comma BDF. And I have ADF, ADF, BCF, BCF, they're exactly the same. So this equals this. So I guess you can't be afraid to calculate a little bit. And so addition of these equivalence classes is associative. And what is the zero? Zero should be 0, 1. If I take the equivalence class of AB plus the equivalence class of 0, 1, I get the equivalence class of A times 1 plus B times 0, comma, B times 1, which is the equivalence class of AB. So this is like the additive identity. Oh, why is addition the commutative? Suppose if I take AB plus CD, I get the equivalence class of AD plus BC, comma, BD. If I add in the opposite order, CD plus AB, I get the equivalence class of BC plus AD, comma, BD. These are equal. So addition is commutative. And if I take the equivalence class of AB plus the equivalence class of minus AB, I get the equivalence class of AB minus AB, comma, B times B, which is the equivalence class of 0 B squared, which is the same as the equivalence class of 0, 1, because 0 equals 0. So for the element A over B, the additive inverse is minus A, comma, B. So what I just proved is if we introduce, let's call it fractional notation. If we write the equivalence class of A over B as A over B, we just proved that A over B plus C over D is AD plus BC over BD, and we have an additive abelian group. And in the notes, I think I worked out everything that one needs to check, that the multiplication is associative, commutative, 1, 1 is the multiplicative identity, And the fact that it's a field, so let's see, let's just check. If I take A comma B and I multiply that by the class of 1 comma 1, this is the class of A times 1 So the way we're defining multiplication is A comma B times C comma D is AC BD. Just like in elementary school, A over B times C over D is AC over BD. So that's the model that we have in mind. And it follows that if I take A over B and I multiply it by the congruence class of 1, 1, I get the class of A times 1, B times 1, which is just AB. So 1, 1 is the unit, it's the identity, it's the multiplicative identity in this set of congruence classes. And if I take AB not equal to 0, so not equal to 0, 1. Okay. 0, 1 is the additive identity. If I take a non-zero equivalence class, which means A is not 0, and we certainly know B is not 0, then if I multiply A over B by B comma A, I get the equivalence class of AB, BA, which is the equivalence class of 1. So AB, that equivalence class, the multiplicative inverse is the equivalence class of BA, which is exactly the same as saying that A over B inverse is B over A in elementary school. So the moral of the story is we can construct a field of fractions from every integral domain. Where is the fact that an integral domain being used? Not just that it's a commutative ring, but when I multiply or add, so here A, B, C, D, I get the pair AC, BD. Because we're an integral domain, if B is non-zero and D is non-zero, then BD is non-zero. So B not equal to 0 and D not equal to 0 implies BD is not 0. Right? This is the definition of an integral domain, and we need this condition to hold for this construction. So what's a nice example beyond the ordinary fractions? Suppose we take R to be the polynomial ring. Let's say all polynomials with real coefficients. This is an integral domain. It's a commutative ring, and if f of x is a polynomial of degree n, degree n means that an is not 0. And if g of x is a polynomial of degree m, which means b sub m is not 0. Then if I multiply f of x times g of x, I'm multiplying these polynomials, I get a polynomial of degree x to the m plus n, where the leading coefficient is a n b sub m, plus lower order terms, and the constant is a0 b0, and a n b m, we know this is non-zero because a and b m were non-zero. And the real numbers are an integral domain. So the product of two non-zero polynomials is non-zero. And the field of fractions are the rational functions, quotients of polynomials. So something like 2x cubed plus 3x minus 5, or x to the 7 plus 9x squared plus 1. This is a rational function. It's one polynomial divided by another. And this is the field. We usually write this as R round brackets x. It's all rational functions in x. So the field of fractions of polynomials is the field of rational functions, right? The inverse, if you look at x squared plus 1 inverse, that has no inverse in the polynomial ring, but in the rational function field, this is 1 over x squared plus 1. This is a very nice rational function, and this times x squared plus 1 is equal to 1. Okay. So this is something that you're not allowed to leave the first course in algebra without learning. That is that if you have an integral domain, there's this construction, which is exactly a model of what you do in elementary school. When you learn how to go from whole numbers to fractions, you're constructing the field of fractions of an integral domain. Any questions about this? Okay. Let's see. I'll be posting more review problems, which we'll go over on Monday, and then the second exam will be a week from today. Questions about anything? No? Okay, then we're done for the day. Thank you all. Be well.
I have a question, Professor.
Yes.
The review for the exam too, when you gonna post? Oh.
Either tonight or tomorrow.
Okay, thank you.
Okay. All right. Bye-bye. Because remember, the homeworks are also review. I mean, that's a good way to be reviewing material. But there will be a separate review sheet that I'll post probably tomorrow. I'm teaching most of today. All right.
Thank you, Professor.
Okay. Bye.